Hello everybody, my name is GraphBG and today we're going to be doing something a little bit more different. I think we can just check out some Java bytecode for a change. So I'm going to leave this in the description. It's the Orcale documentation for the Java virtual machine specification. It's a really good documentation, by the way. And yeah, just check it out if you're doing anything with Java. We're probably going to skip a little bit of the introduction. We're probably going to go straight ahead, go into the structure of the virtual machine. I have worked with Java bytecode before. It's not it's not new to me, but I guess we can just start by maybe making a folder for this. So that's actually going to D S, maybe clear a little bit, and let's go into programming. And let's actually make the Java project and whatnot in Rust. So let's actually make it, what do we call it? Let's do something like, let's actually go into doodles since we're doodling right now. Let's make a directory called Java, Java Explorer, you know. And let's initialize any cargo product, like you always should. Alright, so we got Rust working, and now we should be able to finally initialize a new Rust project. So let's go into D, programming, Rust, doodle, Java exploration. And let's switch to D. And CLS, right? So now we're here. We can just initialize the project, right? And let's check out the source code. So there's this source main RS. So yeah, we have this, right? We have our main entry point. So then we just print hello world. How about we print something else? Hello Java bytecode, for example. Yep, and now if we run it, we get hello Java bytecode, right? So we are going to disable a few errors out of the get-go. So we're going to disable first globally, allow, probably, was it like this, maybe? No, it was like this, allow non-snake case, I feel like it was something like that, right? Yep. And let's just run it. So let's just do cargo run. So unexpected identifier, right? So it's probably this, I imagine. Just kind of disabling the error for the name, because right, the name is a little bit weirder, but I mean it's fine. It doesn't matter. Okay, so I guess the first thing we need to do is probably get some sort of example program working. So I feel like we should have some sort of like hello world made. So let's make a folder called example, right? And let's just do something like hello world dot java. So let's check it out. So we're going to edit, split with example hello world dot java. And I feel like, yeah, let's just write a really basic hello world in Java. And public static void main string args and system out println hello world. So that's our hello world, and let's actually see if it compiles. So yeah, hello world Java, right? And now hello world without the class. By the way, this is a cool thing. Java, the Java command itself, it should not accept .class, right? It doesn't accept .class for some reason. I'm not sure why. We're probably going to learn that from the documentation, but yep. And here we go, right? We have hello world in Java. So I guess the first thing we probably need to do is somehow be able to read from the file. So let's actually provide like a path, which is going to be called example slash, what is it? Hello world dot class. Okay, and that structure we're going to be checking out. And let's just read it into memory, right? So I feel like if we open up Rust docs, Rust.doc, yep. So I'm not sure if there's any like way to turn it into dark theme, because I don't really want to like blind people, but yep, the documentation of the Rust project. So learning Rust, the Rust programming language, and whatever, extensive API documentation. So yeah, let's actually turn into dark theme. Yep. I guess dark, or maybe just this. Right, so that's the standard library. So we get, now let's actually do something like fs, because I feel like fs has something that can read the entire file. Read the entire contents of the file into a byte vector. Yeah, a byte vector. Yeah, exactly what we need. So that's a little bit different from what we're doing, but let's do that. So let's do standard fs read, and we can read the path we provided. So that's path. Probably don't need to add a reference because it's a string reference by default, and it can fail, of course, so we can just expect that it doesn't fail. Expect path. Yep. And now we get some sort of bytes, and we can just log them, right? So we can just log them very quickly. One, and that's our bytes. So we can just do something like bytes. Count bytes. So that's it. And if we run it, we should get. Okay, so it panicked. The system could not find the file specified. Wow, that's actually interesting. So it's example. Right, we're in example, right? So that would explain it. So now if we run it, yep, and we get a bunch of bytes, right? Also, if we just open up quickly the example, let me actually edit the class file and vs with the main file. So as you can see in here, we have some sort of string in here, which is kind of interesting, and then it looks a lot like a source file, right? So we have init, some sort of code section, I imagine, some line number table, the main function, Java string, the source file, the Java file, so like the path to the original file, I imagine, and then we have the string hello world, the hello world something. I imagine this is the class, right? This is the class, and then we have the javalang object, javalang system, out, java io print stream, java io print stream, and I guess that's it, right? So let's check this out. I guess let's actually start by reading the documentation. So the documentation is in here. The Unicode standard version, no references to the Unicode specification, that doesn't matter. The class file format, compiled and executed by the Java virtual machine is class file, the class file format. So chapter 4. Primitive types, a bunch of other information that we don't really need. I want to jump to 4, so where is it? Let's go back and then jump to 4.0, so the class file format, because we're just checking this out. Oh, interesting, right? So now we're starting to get this type of stuff. That's interesting. So yeah. All right, let's check it out. Right, so first 4 bytes are the magic number, right? Let me put this like put this like so. So the first 4 bytes in here are the magic number, right? You see, magic number. So first 4 bytes. So these 4 bytes are the magic number. The magic number is actually the hex value of cafe baby. So now, if we just check this out, like in here, so Python probably, we get this, which if you represent each individual character by a single, you would get a string that should resemble exactly that. So let's see. Let's do char I think was the function ka look fe fe bay be. Look, exactly what we have here. Wait, look at this and look at this. So that proves to us that this is in fact a Java bytecode file. So what we can probably do is now read it. So I feel like there's easier ways to read stuff from you know, files and all that stuff, right, from bytes especially. So you can slice into bytes from a certain range to a certain range, and then I think in the documentation from bytes, yeah, all of these implement from big endian, converts an integer from big endian. N, right? Well, not really, right? So not really, right? And we can just kind of check this out. So yeah, we have probably, like, we want to make I8 from B bytes, big endian bytes, right? Yeah, and that's it. So, well, yeah. Now we can probably do something like, we can define some function that's called like read U32, right? I think, because that's, yeah, 4 times 8. Because like the documentation is a little bit like, it's a weird, right? So some numbers actually so unsigned, and that amount of bytes and not amount of bits. So read U32 from bytes. And what we can do is actually just take some bytes, which to take some bytes is actually going to be a U8, so that's bytes, and we're going to return a U8, right? U32 in this case. And what can we do? Well, we can just bytes do probably the top bytes, so we can just remove the top bytes, and the rest are going to be into somewhere else, but I'm not sure how we can do that. Right, we probably will remove initial n bytes from byte array. Rust, maybe. Well, that doesn't matter. Right, it doesn't matter. We can just have like an offset, but for now we don't really care, right? We don't really care. We're going to slice into them from 0 to 4, right? That's 4 bytes. We're going to probably assert that this is in fact true, and we can just return U32 from bytes, from big endian bytes, or actually Lithuanian, right? I think Lithuanian is the standard, so let's actually do that. So let's get U and just get read U32 from bytes, and I guess that's probably way too long of a name. We can probably just do this, read U32, and it should be enough to now do bytes with a reference, and then just get the result, the magic number. And let's actually print the magic number, right? Because it's kind of interesting, right? So magic, and we can probably do, I think it was X, and you just printed it in hex. Print number in hex, number in hex, rust, into hex. So it's hashtag 0x this. Okay, so that would, now we can do something like hashtag 4, because it's, well, that's hashtag 4, and that's the bytes, I feel like. And let's see, it should probably work. Let's hope at least. And then the cargo run. So yeah, right, we need to do slice. Function arguments are incorrect. So expected for found any. Okay, so alumnus in case the inner attribute doesn't annotate the function. Okay, so yeah, let's actually just have this at the top first, the top of the file, and run it once again. The argument of this function are incorrect, and yeah, well, we need to convert from U832 from U8 to U8 form. Convert slice. Alright. Console size, try from, and start in library. Range, doesn't matter. I guess, yeah, in this example, they do split that. Okay, well, that makes sense. So now we can just do something like mutable bytes. Those are the bytes. And then we can just do bytes, split that. Okay. Bytes, split at. Where? Split it. Well, we just need 1. So that's size, which is 1. Or in this case 4, because it's 4 bytes. And then just... Alright. And that returns something like rest and... Okay. And we can now just have... Okay, so that's the int bytes, so that's try into, then unwrap. So that's, yeah, that makes sense. So b, and now we can just do something like bytes is equal to rest, right? And then we can just return this stuff. Essentially, it's b dot try into, then unwrap. It should work, right? And if it doesn't work, right? It doesn't matter. So we're expecting a U32 found and nothing. Oh, right, because it's, we will put this in here, and that doesn't really matter for us. I can probably close this as well. Mismatch types, mutability, right? So we need to do let mutable bytes, mutable bytes. So that's it. Found vector. Well, a vector can actually probably be turned into that, into unwrap. Or maybe we can just do something like mutable and then a reference to it. So this. Well, we're getting closer, right? We're getting closer. We want to do that. Which is kind of a little bit more difficult. Vector to slice, vector slice rest, vector to slice. So we have this. So you need just to do this, right? So we just do this. That should be it. Babe, cafe. Okay, so it's backwards, which would mean it's not le bytes, it's actually b bytes. It's big Indian bytes, which would mean cafe babe. Right, and we get the magic number, exactly like we want it to. Right, we don't really need it to be mutable. I guess it doesn't need to be mutable for some reason. It says mutability, remove mutable. Sure, I mean, I don't mind, okay? So now that's the magic number. Right, and then the next part of the structure is what? The next part of the structure is the minor version and the major version, which I guess we can just tuck into its own another function now, which is called read u16. Right, so 16, split at 2, and that's the rest, and that's u16 from bytes, b bytes. And I guess then we need the console info, CP info, U2, access byte, and a lot of other stuff. Right, so but for now, let's actually do something like major version, which is read U16 out of this. Alright, and now major, and now minor version. Right, I think it was like that. No, it was the other way around. So no, oh, actually, yeah. It's a minor and then major. So minor version, minor, major. Alright, and then we can actually print them the minor version and the major version. So that would be, we can just do something like version. Right, so that's minor version. That's major version, I guess. Major version and minor version. And now if we run this, okay, is that wouldn't be it? Wait, let me see something. Let's actually do pi. Exactly it. So that's wrong, right? So we need to do we need to have some sort of offset, right? We need to split it and then write back to it. So I guess you can actually have like an offset, which is maybe called a cursor, right? Which is called a U32 cursor. Or maybe we can, instead of accepting this, we can accept a mutable vector U8 and then change this back into it. So mutable, and then we can do vector of U8, which would be close to what we want, right? I guess. Okay. And let's see if we get anything. So that's rest to vector. So it's expected vector of U8. Maybe split that, but with the owned one. I mean, I'm not sure. Maybe we can just do something like, let's split it to. We first need to make this mutable, of course. But we also get rest try conversion, right? Well, we don't really want to split that owned, maybe. Let's actually check in the documentation. Let's split maybe. String split, vector split off. It returns TA and then A. Split off 1, which would get, yeah, that's it. So that's split off. So we just need to split off, right? That should actually be a lot easier for us to do. And that should be it. So maybe split off this expression. Expected vector U8 found this. Okay. Split off 1, and then the original vector changes. So we just do B, right? We don't need to write it back. We just get B, right? We don't need to write this, and now we can just do, yeah, that's actually a lot simpler than what we did before. So we can just take this, it's here, paste, split off 4, and that's a U32. Right, you probably want to have a template and then just have accept the type, but it doesn't matter, right? So environment variable display a backtrace, didn't successfully, result on unwrapped value 000, a lot of other stuff. Okay, sure, right, sure. Run rust backtrace equals to 1 to check the, oh, right, so that's actually on error value, so that's weird, right? So from bytes. Maybe. Alright, that's kind of interesting. So it did work, and at line 4 it panicked over here. So let's actually log what B is. Let's print line B. Well, let's do B. Alright, and let's see. Let's actually do something. Come on. Mismatch types, expected that. Okay. From B bytes can actually fail, so now we can just unwrap it in here. I don't know why it would fail, but sure. COS, right? So cargo. No method named unwrap for okay. Well, sure. Here you have it. From big bytes being to expected EU32 found. Oh right, so yeah, that's 32. I'm sorry. Sleepy, right? So okay, so B is the huge one, and what about okay, let's do bytes. Bytes. So bytes is the one we want. When we need to swap them, kind of split off. So split off. So we need to kind of split it, right? One, and then the return vector is actually the old one, and this vector is this one. It seems a little weird, right? To me, personally. Alright, so let's... okay. Maybe there's something like split vector split. Split at spare mutable. This is a nightly feature. No, frick you nightly. Split off. Mutable. No, it returns itself. So that's... yeah, that's exactly what... no, that's not what we need. So... alright. It's a little weird. So, essentially, bytes should be equal to this. But then the original bytes should actually kind of... so let's actually do underscore B. And then we can just do bytes. Underscore C equal to the bytes, and then bytes, not dereferenced, is equal to underscore B. So we can swap them around. And then underscore C, which is actually the new B, so that's old. I guess rest maybe. And then the bytes are equal to the rest. This is probably not gonna work. It doesn't implement copy. Consider removing the reference. Dereference cannot move out of the mutable reference. Well, swap within a reference. Rust, we need to kind of swap the mutable references. Is there a way to do that? Yep, seconds. Mem swap, right? Yeah. Standard mem swap, right? So we can use this standard mem swap. So we can swap the okay, so we can swap bytes with rest. We need to call rest. So now we should, rest should actually have the ones we need. So now we can do rest try into. If that works, I'm going to be very much amazed, because it seems really annoying to do this way. U32 instead, and that's 4 bytes. Cannot borrow because it's not marked immutable. Okay, sure. Sure. CLS, and let's run it. And it actually works. So the version is 55.0. Okay, minor version, major version. The values of minor version and major version items are the minor and major version numbers in the class file. Together, a major and minor version number determine the version of the class file format. If the class file format has a major version number m and a minor version number lowercase m, we denote the version of the class with m.n. So we need to do m dot, actually it's m and sure, 55.0. Okay. The file format version range from 45 to 44 inclusive. So yeah, we have a really new one, so that's 55.0. Okay, that's kind of cool. Then we have the constant pool count, so let's actually get the constant pool count. Const pool count equal to read u16 mutable bytes, right? So you want to read another few bytes, so that's the constant pool count, and we can just do something constant pool count. Constant pool count, which would be equal to what? To const pool count, and let's run it. So that's 29, right? So now we have the pool, the constant pool, which is cp_info. So let's actually search for cp_info now within the file. So that's the tag and then the info. So we have different types of tags. 1 byte, so that's cp_info. Tag indicating the type of the cp_info registry. So now we can actually separate this out to its own separate structure. We can probably also separate the other stuff into its own separate structure, right? So we can have the struct called the Java header, right? This is how you abstract away some stuff. Like, look, we had all these variables, now we can actually abstract them away. So we can have the magic number, which is a U32. We have the minor version, which is going to be U32, U16, I guess. And a major version, which is also U16. And then we can have the constant pool count, which is going to be a U16. And I guess, like, if we're translating it one-to-one, this is how you do it, right? This is how you do it. But I feel like in Rust, since we have vectors, which it's a lot easier to just make constant pool, which is going to be a vector of cp_info, right? And let's actually define some cp_info. So struct cp_info, and let's actually use the format that we, so Pascal case, we're going to be using Pascal case in this case. So cp_info would have a tag which is going to be u8, and we're going to have a few constants for tags. Okay, it has different types of values. I don't know why they don't order them in the order that they should be, which is going to be a vector of u8, right, for the bytes. And then you can interpret those bytes in a certain way, which is actually what we need. That's kind of cool. Okay, so now we have the cp_info. The thing is, we can't really read it until we know the sizes of these, and they have varying sizes in an interface. So it would be a lot easier if we could just have a vector of what's called as what? Const info. And a const info should be just an enum const info for the different types of const info. So you'd have one for the constant class, so that would be class. You'd have the class info and whatnot. So yeah, now you don't need the tag anymore, because the const info should hold the tag itself. Or at least parse it, right? You would have now the tags in here, you would just assign different stuff to the const info. And yeah, so now you can just see to have a const info. And that's actually really simple to do, which you don't ever need now cp_info, because you just do that, right? So you can just do that. Okay, and we have different stuff, and now we can just kind of copy these, paste them into here, go like this, and just add this like so. We don't really need, yeah, we can just do something like I guess we can just define them as constants, so we can just do something like delete inside const, right? So that's it. Let's insert some more spaces that it's easier to declare them. Alright, and then we can just add a bunch of spaces. Why do you add so many spaces? But because, well, we need to kind of then do this. Okay, need to do equals, probably a space, and then we just do and this. Okay, so that's annoying. We need to select these guys. Come on, insert, comma, you. Okay, we need another space, get another space. Insert, comma, right, and that's it. Control V delete. So yeah, we didn't insert them here because it's annoying. Vim is annoying. Right. So we can just, instead of doing this, we can just take this and remove them. Alright. So we have a lot of stuff. I don't think we're going to be handling all of them. It doesn't at least make sense to handle all of them. Also, what the fuck do I have constant in here? Okay. Class. Let's actually start with the first one and actually order them in a descending order. So, or I guess let's actually look at them from a documentation standpoint. Right now we don't really have anything for const, but we can just have like a D, which is a U8 for now. Just temporary stuff right now. So then you can just implement const info fn read from bytes, and you just have some bytes, which is called a mutable vector of U8 as always, and then U32 in here, U32 from bytes. Oh yes, from bytes directly. So then you just do something like, I guess it's going to return a self, right? So it's going to take the bytes and it's going to return a self, and it's going to then do something like, let's actually do this a little bit more down. Probably take everything in here and just move it a lot more down here, right? Because we want to kind of not intervene with these functions, which are base functions. We can just do something like from bytes, we can just do read U8 now. So there's a tag. Yank this, paste U8, and that's 1, right? So now we can actually read the tag, right? And we can just read the tag. Read U8, and then we just provide the bytes directly. And you just get the tag, and you can just do switch, and I guess match the tag, and then defaults. I guess default was what was this. Eprintln unhandled Hispanic unhandled tag %me tag. Okay, and then you just do something like for I in 0 to const pool count, and we can just collect them into a vector of constant info. I guess yeah, let's just make the header first. So we just do something like mutable header, which is going to be a job header, right? And that's going to be, let's actually derive default, hashtag derive default, because I'm going to add a lot of stuff to the structure and defaults. It's really simple to do this instead. So now we can just do something like, all right, header, instead of magic stuff, I can just do something like header dots, magic, and all the other stuff. Now we can just keep the printing going, so we can just do header dot the major version, header minor version, and header. I guess that's not really in it. Okay. And constant pull count, and then you can just do something like I guess header dot push back. I guess push was it? I feel like it was push, and then we can just do constant fo from bytes. And we can just give it the mutable bytes, and that should read it, right? And that's now the constant pull count. So we can visualize the pull. Const pull, I guess. That's going to be our header constant pull. Alright, constant pull. Header dot constant pull. And you can just print it with debug printing, right? So that's it. Okay. And we have a lot of problems, right? Missing tag definition. So it's tag. So when it's tagged, we need to do this: insert u8 space. All right. It looks horrendous, but yeah. Let's actually do this. And yeah, let's actually do hashtag derived debug, because it's easier, right, to use hashtag derived debug in this case, CLS, and let's run it. So then remove the semicolon in 57, line 57. Why does it complain about semicolons? I mean, it should complain about the lack of semicolons. It's not really this one, okay? Expected I6, yep. That makes sense. Yeah, on u8 COS. So yes, yeah. Unused constant. Can I actually do something like unused? Allow that code. Again, you shouldn't probably be doing this in production. That code, because right, you shouldn't really doing stuff like this in production. Okay, why are you? Where are unused variables? Allow unused variable. An S variables. So now we can just clear the screen and run it. Again, why do we get this kind of stuff? Non-uppercase globals. My fucking god. I guess we can just do something like Control V, come on, Control V, delete V, insert tag, and then we can just do this, and then just go like this, and then we do upper, and use all, that's upper, and let's just add some spaces as well, so that it's aligned, right, and it looks kind of semi-cool, I guess. That's it. Yeah, dynamic. Yeah, that makes sense, right? So that's it, and that's no errors. We get no errors, and we panicked it. Environmental variable, environmental backtrace, press on handle tag 10. So the first tag we ever get is 10, which is method reference. Cool. So we can now. By the way, this is how you usually do this, like especially this function. I want you to pay attention to this function. As you can see in here, we're basically doing the exact same tactic as you would do in a lot of other stuff, like especially on VMs and stuff. You have a bunch of instructions, for example, for a Game Boy. You have all of them, and you shouldn't be implementing all of them. If you're just trying to implement some sort of game, or even if you're just implementing the Game Boy itself, don't implement the instructions right away. because it's time consuming and you're not going to see anything and you're just going to be super demotivated. So what you do is you just assert false, or like you just have a panic in this case, where you have unhandled tag, right? Unhandled tag. And then once your Game Boy reaches that state in which it can't really execute the instruction because it doesn't know what it is, you're going to know that, and then you're going to check the manual, get the instruction, and then implement the instruction itself, move on until you get to the next one, and at the end of the day, you're going to just implement the entire Game Boy without even knowing it, because you just implemented all the instructions, and now you have a working game. And even if that game doesn't use all the instructions, you can always just kind of go in and just like just implement like another game, right? So, and do the exact same thing, and you've already got a working virtual machine for running the game, right? So in this case we have 10, and we should consult with documentation, method ref. Like, as you can see here, we don't really need to bother about the other tags and implementing all of them and reading all of them, because we don't really get to them, right? So let's actually do constant class info. Let's actually do constant method ref info. Okay, so the method ref info is this, right? So that's it. And now we don't need you anymore. So that's method, I guess. Method ref. Which is almost like what you would write in here. You would just do something like u16, right? U16 class index, and then name index u16, u16, and that's it, right? You have this, and now that's method ref. And now what you should do is just parse the method refs. You just do read the to u8. So you just do self method ref class index read u16 of bytes. And again, you should probably have some handling for errors, like in here, if you go out of bounds or the bytes end, you just need to have that. But again, this is just testing, right? Name and type index. Okay, read u8 u16 bytes. Is that it? I don't think it should have the tag. Should be okay. So we need a tag as well. So that's a tag, which is a u8. We don't know anything about the tag, as you can see. We don't know shit about the tag. But just because we know how the structure looks like, we can already parse it, right? So now we've got it implemented. Next thing, unhandled tag 0. Okay, that's a little bit weird. So is it... Oh, okay, so no, it doesn't have a tag. Is that correct? I hope so. Aha, yeah, now it's correct. So tag, that's a really deceiving one. Tag shouldn't be here. Tag shouldn't be here. I didn't need it. Okay. Next one is 9. 9 is what? 9 is tag field ref, right? See, I copy this, paste it here. Look. We just take this, and now we have a field ref. I don't know anything about this, right? I don't know anything about this, but just because of the fact that I have this whole system, I can just copy the information over here and just implement it. So we need to have a class index. It's going to be u16, and then a name and index, name and type index. Okay, name and type index, another u16. Right? Look at it. Look at this. Like this is how you develop a really good habit for building like virtual machines and building all kinds of cool stuff. Not exactly virtual machines. Well, maybe, but right. And I can already see some stuff like method ref. So that's calling to I imagine print stream, and then it has field ref, which is giving it one of the fields, and now it's getting the string. So we're already seeing some patterns, which we should remember. Tag string. So now what we can do is actually take the string info. Yep, string info. Right, and it just has a tag and a string index. That's it. Very simple. String. Oh, we can just do. We can do this like string like this. Why do we just have an index? Which is a string index, which is going to be u16. And then just return self string index, which is going to be read u16 bytes. Alright, we implemented that. You don't even need to do this, by the way. You can just probably do this. There's actually a lot more ergonomic. Oh, not really ergonomic. Like, this is actually the exact opposite. It's not very ergonomic if you want to expand it, but it doesn't matter, right? So you can just, it's a lot cleaner looking, what I was supposed to say in this case. And right, look at it. It's tag 7. Tag 7, which is this, right? It's a tag class. So we can just do tag class. And that's going to be the subclass stuff. That's the class info. So class info. Come on. Class info. Can I look at it? Thank you. So it has a name index, so that's it. So that's class, I guess. Name index in 16. So then we just return a self-class. That's going to be the name index. Which is going to be read u16 bytes. And now we just have the name index, and that's the class. Parsed. Next thing, tag 1, which is tag UTF-8. Right, so tag UTF-8. Yes, that's UTF-8. Then you have sort of structure, and then you just do tag UTF-8. And what can you do? And then you just need to find the UTF-8 info. Alright, so that's length and then bytes, which is length. Okay, that's a little bit weird, right? But it's fine. So then we can just do something like okay, so that's gonna take a little bit more stuff than the normal ones because it has like the length, which I guess for now, I guess it doesn't really matter because in Rust, in the arrays, we actually store that, so that's actually bytes maybe. So then you can just kind of read the bytes, so length, which is going to be a read u16 out of bytes, and then you can just read some bytes. So fn read bytes, n, so you have like the bytes, immutable vector u8, and you have n, which is going to be a usize maybe, and it's going to be return a vector u8, which is just this split off at n, and that's just the rest, and then swap, and you just return rest, and that's it. And then you just do read bytes, and you can just return self UTF-8 bytes as read bytes, of length. Read bytes length. Right. Very simple, very elegant. Oh, we have mismatch types. We need to add the size. Okay, and now we've parsed the UTF-8. We have tag 12, which is a name and type. Name and type. Tag and name and type. So name and type info structure. So that's tag. We have the name index and then the descriptor index. That's name and type. Name and type. Name type. Because I want to make it a little bit shorter, or maybe just name type. Alright, and that's the name index, which is going to be a 16, and then the descriptor index going to be another U16. Okay, and then just do, instead of that, just return self-name type, which is just name index. You read U16 bytes, and then the descriptor index, which is the read U16 bytes. As you can see, we don't really we're not handling any of them. We're just parsing, but that's the first step, right? And now we have tag 0, which is an invalid tag. We write something is wrong. Descriptor index. That's a little bit wrong. Okay, so that makes sense. Okay, so we've reached the end, but it's -1. And look what we got. I guess what we can do is actually pretty print it. Is there like a pretty printer like this? Yep. So we have a bunch of UTF-8 stuff. You have the method reference, the string, the method reference, the class name, then some UTF-8, and then the UTF-8. A lot of bytes, and a lot of bytes, right? So a whole lot of stuff. And yeah, name type index, the class, the name type index, UTF-8, class index, and a lot of other stuff. Alright, that's kind of cool. Oh, we parse the constant pool. That's simple. Let's go to the top here. Okay, we've parsed the constant pool. Then we have the access flags. So access flags, which is going to be U16. In this class, which is going to be U16. The super class, which is going to also be U16. The interface count, which we're going to parse at some point, but not right now. This class and all that stuff. So now we've parsed the constant pool, and then we can start parsing the other stuff. So then we can just do U16, since they're U16, we can just do read from the bytes, and that's actually going to be this class and this class. And this is actually going to be called the superclass, right? Superclass. Redo. Superclass. And then we have the parsing of the interfaces. We can even log this, but we don't really care. Right, so log the version and minor version, flags, access flags from the annotation of this stuff. So I guess we can actually log it in hex, so we can just something like access flags, right? We also need the access flags. Access flags equal to read U16 mutable bytes. Alright, and then we can just access flags, this class, superclass. So we can log this now, this information. Now that we have it, we can just log something like access flags, which is going to be hashtag 4x, actually 2x because it's 2 bytes, so that's header access flags, then this class and this super class, so we can just log it normally. This class super class access flags, we can probably gospel count, and that's okay. And now we can just use that instead. So yeah, constable count. Constable, we don't really need to print it, right? We don't really need to print it, but access flags, this class, and superclass, right? That's it. And let's see what we get, right? So let's run it. And we get this class, which is 33, and the superclass, which is also 33. And then the access flags is 0x21, which let's actually log this in access flags. Wait, let me see. So the access flags are also U2, so I don't know why it's represented this way, but sure. What about 4x? Maybe that's going to be a little bit easier for us to see. It doesn't matter. So 0x21. 0x21. So 0x21, right? 0x21. If we open a Python, okay, so first let's fix the typo. So it's access flags with double C. And let's run it once again. Okay. Okay, so Python access equal to 0x21, right? And we can check if it's public by ANDing it with 0x001. So that's we can do access or and 0x001. Okay. And that's for final. It's not final, right? That makes sense. It's a superclass. Treat superclass method especially when invoked by the invoke special instruction. I don't care too much about this. It's 0, so it's not an interface. It's 4 if it's abstract. It's not synthetic. It's not an annotation, and it's on the enums, so all of these should be false, right? So it's just a public and then it's a final. So now it's a public and it's not final. It's public, but it's also a superclass, so it's a super attributes, super access stuff. That's kind of cool, right? So we can keep the exact same stuff for our other, like, if we're ever going to check out, like, generate some class files, we should keep this in mind. So then what can we do? Now we have the constant pool. We have first a lot of yields and an interface count. Now we need to parse the interface, so we can just do something like interface. Let interface count is going to be equal to the read E16, the mutable bytes. Interface count. Interface count. We can just print interface count after it. In here. Interface count. And then just do interface count. Right, so now we have the interface count. And let's parse the interfaces, right? So actually interfaces are just a bunch of U of 8s. So let's actually check this out. Each value in the interface array must be a valid index in the constant pool table. So that doesn't really bother us at all. So we can just, yeah. So I guess we can just kind of collect it into a vector of U8s. I'm not sure, right? So let's see. Interface counts, we don't really care about it. Now we can have interfaces. Interfaces are going to be a vector of U8, U16s, I guess. And what we can do is actually do the exact same thing as you would do in the case, but just in case, right? We have we have knowledge on what the constant pool looks like, so let's be a little bit more efficient, right? I think there was something like reserve const pool count -1. So let's just be a little bit better with our memory, right? A little bit better with our memory. So now we can just reserve also a little bit of memory for the interfaces faces. So now I in 0 const, so that's interface count. We have 0 interfaces, so that shouldn't bother us. Interface count, but just in case, we're going to just push back some stuff. So header interfaces push back read u8 u16, I guess mutable bytes. This is a little bit less efficient, right? You should probably just have like chip away the different parts and then just interpret it as a vector u16 instead of a vector u8, but it doesn't matter, right? It doesn't matter. We're not doing this to be efficient, right? Okay. Just noticed something funny. Alright. Okay, so yeah. And then we have the fields count. So fields count, cool. Fields count. I'm going to be equal to read u16 mutable bytes. Let's actually check out if everything in our code works. Okay, it doesn't exactly, but so reserve interface count -1, so -1 as usize, so you can just interpret that as usize, and this as well as usize, since it's a bit easier. So yeah, all right. So now that we have that, we can probably just run it and see what happens. So it's no method found in. Okay, so it's not pushback. I'm sorry. C++ is getting back to me. So attempt to subtract with overflow. Okay. Why are you doing this? Like, actually, Java, what is wrong with you? Cool. Alright, cool. Well, yes, it makes sense. So there's at least something in the constant pool, so they can assume it's +1, but why would you ever assume it's +1, right? Even if it can be with, like, it can't be with 0, right? It doesn't matter, okay? It doesn't matter. Okay, so now we have the fields count. Now we need the field info. Okay, we're getting into the new stuff. So field info structure. Can I actually check out the field info structure? Fields, field info, we have attribute info. That's kind of cool. So we have field info. We have the access flag like before. Okay, that's kind of cool. So now we can actually have the fields as just the vector of field info. So that's the field info structure. Let me actually look into the bytes of this of attribute info. Info. Come on. Okay, so that's it. It doesn't matter. Yeah, it doesn't matter. Keep. Alright, so now we can just have something like a struct code. How do I call this? We call this field info. And field info is actually going to have first, right, the access flags. So access flags is going to be u16. Then the name index is going to be u16 as well. And then we have the descriptor index which is going to be u16. And then the attributes count, and the attributes, which is going to be a vector of attribute info. And now I can actually define an attribute info. That's kind of cool. Okay, and that's it. So we can just Then now attribute info. Can I check out attribute info? Right, attribute info is this. So it's an attribute to name and index. Let's actually copy this. Paste. So that's attribute length. So that's okay. That's a U16. We need to keep that. The length we don't need to keep. And then the info is just a bunch of bytes. So info is actually going to be a vector of U8. Alright, vector of U8. Okay, so I just had a little bit of a cut here. For I in 0 to fields, so fields are reserves. So that's header fields reserve. I'm going to reserve fields count, I guess, as you size. Why? Because in here in the documentation they say, right, fields, which is a field info of the okay, that makes sense. And now let's go into field info. Okay, I don't know where I'm at currently. Okay, let's check out what rate we reserve that, and then we just do something like for I in 0, already started, still fields count. We can just do header fields push field info from bytes, which is going to be mutable bytes, right? So now we can implement here field info, which is going to be from bytes, and from bytes, which is going to have a mutable bytes, I guess bytes, which is a mutable reference to a vector of U8, right? It's supposed to return self. This is going to do something like, okay, we're going to do let result self, default, we can derive default, self default, let's mutable self because we're going to changing it, and then we can just do result dot access flags equal to read U16 of bytes, right? And then we not only have the access, but we have the name index, the result descriptor index is going to be equal to okay, we're going to be equal to read U16 of bytes. And let's check out the attributes. So attributes count. That's yes, okay, that makes sense. Attributes count, which you can just read the U16 out of the bytes. Okay, and then we just do result reserve utter count as usize, and then for I in 0 to utter count, we can just do result push attribute info from bytes, and that's it. And then we can just return results. So that's it. And now we just do implement attribute info, which is also going to have from bytes. So derive default because it's easier that way. Fn from bytes mutable vector of U8, and then that's going to return a self. Let mutable result equal to self default, and then result attribute name index equal to read u16 bytes, and I feel like I remember that it was me attribute info. Just let me check out attribute info. Attribute info, that's 8 for attribute length. Okay, that's a series, okay? Makes sense. Array length equal to read u32 bytes. And then we can just do something like result.info equal to read u16, so that's read bytes of bytes, and then array length as u6. It was like that, right? Okay, it was like that. And then you just return result, right? So that makes sense. And that's it, right? That should be everything. And let's see the errors. Okay, let's first check out 0. So attribute name and index. Here should have a comma, and this should need to have that. COS, cargo run, methods reserved. So here we're missing this, and then we run it once again. Attribute name and index. Huh? Wait, what? Ah, okay, so we need to run it. Okay, sure. COS, right, cargo run. Field info. Okay, we need to do dot attributes reserve. So we're reserving the attributes, and we run it, and there's no method push because it's attributes. Where is the issue? 101. Okay, attributes. Okay, that's kind of cool. Interface count makes sense. Right, makes sense. Interface count, just 0, and then it's a field count. We can log it in. Print one field count, which is going to be a field count type. All right, that makes sense. 0 fields. I mean, sure. All right, and then what do we do? We have a bunch of attributes. Doesn't matter. I'm going to check them out later. Or actually, we're going to check them out now. Right. Ooh. Wow, so yeah, we have a bunch of attributes. We don't need to check them out right now, right? We just need to get the information for them. So let's get back to the top, the structure. So in here we have the methods count. We need the methods count. So let's do let methods count equal to read u16 of mutable bytes. Right, that makes sense. And we can even print them, right? Methods count, and we can just do methods count, just like so. We have 2 methods, right? That's kind of cool. Here's the methods count is also like that. So let's just do for I in 0 to methods count. Let's actually do something like header methods reserve methods count as you say, and let's do methods now. And methods, which is going to be a vector method info. Okay, method info. Method info structure. Can I see it? Okay, that's kind of cool. It's a method info. Let's actually implement that. So that's method info, and then we hashtag derive default. We're going to do. So cool. We have the access flags. Access flags as always. We have the name index. Also use 16. The descriptor index, and let's actually just copy this, right? Come on. Okay, that makes sense. And now we have the name index, the descriptor index, so here use 16. And the attribute count. It's going to be 16. Or yes, attributes. Which brings the vector of attribute info. Alright, and now we have the method info. Method count, header methods, push method info from bytes, mutable bytes. Alright. Okay. Push back the methods. And now we need to implement from bytes. I'll use 8. And you can just do something like this. So let's copy this. Results. So we have the access flag, the name index, the descriptor index. Why do you need different structures for this? I have no idea. Right, but that's it. That's essentially the exact same thing. And now we should parse it correctly. Okay, so now we need to return some. Makes sense. Plus, we have two methods and we've already parsed them. And yeah. Cool. Okay, so yeah. Let's go back to the structure. Right, back to the structure, and you have the attributes count and then the attributes. Okay, that's actually fairly simple, right? So attributes, we're going to go vector of attribute info, right? So you have attributes, and you have header attributes reserve, attribute count, that's the size, and you can just do let attribute count equal to read u16 and mutable bytes. Right, and that's going to get us the attribute count. And what can we do? We can just, I don't know, for I'm 0, just iterate over what we do usually and just push them back. So push back the attributes, attribute info from bytes, mutable bytes. And I guess that's it, and that's it. That's basically all of it, and then we can just do something like assert if, or maybe just if I can print the attribute count. That's it. So if bytes with 1 and 0, then we can just do something like you print ln valid Java bytecode should have parsed everything up to here. So that means that the header itself is actually kind of long, so let's actually do do here, and we can just do this one. Standard process exit one. Okay, and that's it. So yeah, so it's not a header really, it's a Java body class. Java body. Okay, so it's Java body, and this is Java body. Right, and now instead of header, we can just replace the header with substitute slash header with body. Yep. Also do it for this one. That's body. Alright, and we've kind of parsed it, so that's kind of cool, I guess. Now we can actually log some stuff and get some information. But now we have the version ID, the constable count, the access flags, the disk class, superclass, interface count, fields count, method count, and then the attributes count. That's kind of cool, right? That's kind of interesting. So yeah, if now it would be really nice if we could just log the body itself. Body, that's the Java body, and I don't think it implements it in debug, so let's actually do debug as well, and let's just print it. Let's print it as it would look by default. So this needs to also have the derived debug attribute info, debug as well. So that's debug. Okay, COS, let's actually do this. So then the next one is fields, debug, COS, and then just run it again, and that's debug for method info. It should actually derive debug as well. Okay, and COS, and then just run it, and we get a bunch of stuff. It doesn't really look great, so let's do this instead. Have a bunch of attributes which don't really mean anything right now. Right, they don't really mean anything currently, but right. This is, I guess, a little bit cool. So we have the class index, and we have a name and type index, and a lot of stuff. But again, this is not really useful, right? This is not particularly useful. Because, well, like if we can't really see the methods and their attributes, it's not really all that useful. But we managed to parse it, right? And that was basically the purpose of this video, right? Just learning a little bit more about the attributes and how the class file structure looks like. And I guess for now we can probably just, I don't know, print the UTF-8 strings correctly and go from there. Yes, we can probably just select that we can kind of clean this up. Even with more advanced stuff, we can already print some nice information about them. Alright, we already have a lot of information about them. Now we just need to, if we want to parse even, if you just take this program and want to parse all of these, just open up the docs, search for these names, find what they are, and just implement them into the constant table. And that's it. It's that simple. It's so kind of cool. I'll just clean this off camera, and I guess that's it. So if you guys enjoyed this video, don't forget to subscribe, like the video, leave a comment for suggestions of what we can do with this, and I'll see you guys in the next video. Bye!